Trigonometry, Chapter 7, Applications of Trigonometry, Vectors, Section 1, Oblique Triangles and the Law of Sines, Video 3, Deriving the Law of Sines. This series is based on content from Pearson's Trigonometry, 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we solved the following oblique triangle problem. In triangle ABC, suppose a measure of angle A is 32.0 degrees, measure of angle B is 81.8 degrees, and A equals 42.9 centimeters. Find the length of side B. We solved to get B equals 42.9 times sine of 81.8 degrees over sine of 32.0 degrees. We observed the original given values, the ones in blue, were intact in this expression. In this video, we replicate the process to derive the law of sines. Now, to do this, we have to remove all the specific values and attack this generically. So no numbers, just triangle ABC. Now, for convenience, we shall use the same notation to represent an object and its measure. In higher level math, this is a no-no. You can't use one thing to represent an object and how large the object is. But for the sake of convenience, we will. So when we say A, that will represent both this angle and its measure. Now, let's assume we know the values of side A, and angle B, all highlighted in yellow, and we wish to solve for side B. As before, without the assumption of a right triangle, we cannot arbitrarily set up a trig function. So to accommodate, we draw segment CD perpendicular to AB, where D is on AB. So we do the same thing we did before. Now, for convenience, we're going to label the length of side CD, segment CD, with H, which of course stands for height in this picture. Now, before we continue, we should point out that CD, this segment, is inside triangle ACB. This is merely a consequence of how we chose to draw the triangle. If either angle A or angle B had been obtuse and we dropped a perpendicular from C, then CD would have been on the exterior of the triangle. We'll handle that case later. For now, let's assume A and B are acute so that CD is actually on the interior of the triangle. Now, as with the example in the previous video, we're going to start with triangle BCD because we know two of its measures and then we can find side H, and then we're going to jump over to the other triangle. Now, in triangle BCD on the right, since H is opposite of B and A is the hypotenuse, we can immediately set up sine of B equals H over A. That's just standard right triangle trigonometry on triangle BCD. Solving for H by multiplying both sides by A, well, by multiplying both sides of this by A, would give us H equals A times sine of B. We'll bring that back in a moment. Now, on the other triangle, ACD, we similarly set up the following equation. Sine of A equals H over B, because sine in a right triangle is opposite, which is H, over hypotenuse, which is B. Now, instead of solving for B, which really isn't really our goal, I know it said it back here. It said where was it? Solve for B. We're really trying to set up a relationship. So solving for B is not really critical. What's critical is getting an equation that contains angles A and B and sides A and B. So let's go ahead and substitute A sine of B for H inside of this equation, which gives us sine of A equals A sine of B over B. Now, let's get rid of the picture and clean it up. Is this the law of sines? Well, sort of. But we're going to make two adjustments to it. Number one is to make it pretty. We're going to manipulate the equation so that the letters on the left are the same and the letters on the right are the same. Now notice all the B's are already on the right. Sine of angle B on top, side B on bottom. So we're going to get all the A's on the left. And we can do that by just dividing both sides by side A, lowercase a. That will cancel the A on the right and put it underneath sine of A on the left. This looks much better. Sine of A over A equals sine of B over B. Is that the law of sines? Well, again, sort of. So why is it not? Well, because second, our choice of focusing on A's and B's was arbitrary. If we go back to this picture where we started, I could have given you any two sides and their opposite angles. I could have given you A's and B's, which I did, A's and C's, which I didn't, or B's and C's, which I didn't. So our choice for A and B was somewhat arbitrary. Now, as such, we could have ended up with any two of three similar ratios involving two of A's, B's, and C's. In other words, we could have done A's and C's or B's and C's or A's and B's and gotten pretty much the exact same result. So to account for this, we simply create a double equation with a third ratio similarly structured for the C's. So we have sine of A over A equals sine of B over B, and we'll throw in a third one for sine of C over C. Again, this is because our choice of A, B, and C was completely arbitrary. We could have picked any two and gotten the same results. This is the common version of the law of sines. Sine of A over A equals sine of B over B equals sine of C over C. Another way to phrase it is in any triangle, the sine of an angle divided by the length of the opposite side is constant. You can also have the reciprocal version, which puts the signs on the bottom. One last comment. In the case that an angle is obtuse, let's say angle A, the approach does have to be modified because side CD is on the exterior of the triangle. Now, this is pretty tricky to follow, but I think you can do it. In triangle BCD, everything proceeds as before. Sine of B is H over A. But in triangle ACD, notice that angle CAD, this angle in the green triangle, is not an angle in the original ABC triangle. It's what's called an exterior angle for the triangle. So when we set up the trig, okay, so the purple one is the angle A inside the triangle, and the blue one is the supplement of it on the exterior of the triangle. So we have to use the green triangle because it has the right angle. So we have this blue angle and we have this purple angle. We want the purple angle, but we have the blue angle inside of the right triangle. Now, those are supplements, which means their signs are equal. Can you verify that? This means that when sine is applied to angle CAD, we can eventually replace sine of CAD with sine of CAB and eventually arrive at the same law of sines as before. So it doesn't matter if A or B is obtuse. That simply means that we have to deal with the supplementary angle of that obtuse angle, but their signs are equal, and therefore the law of sines would follow through as well. I know it's a mouthful, but just know the law of sines because that's the important thing in this video. There is no now you try for this video. Just know the law of sines. It's pretty easy to remember.